really want to thank Professor Bronstedt about setting up the stage for me to talk about some of the sediment dynamics, and especially coming out from the Indian Himalayan region. And as Professor Bronstedt talked about and touched that, okay, how the sediment, the last slide, okay, why it is important, and sediment transport is one of the area which we do not really have understanding, but also it is basically a lot of there is an impact, but also there is a need to collect those type of data from this type of mountain system. So as you all basically been hearing, and we have been sitting in a natural hazard symposium. So when we have these natural hazards, and as Professor Bonson mentioned that okay, the glaciers are melting. So glaciers melt, but there are other natural hazards which are occurring very frequently in Indian Himalayan region and other mountain system is the glacier lake outburst floods. Also, the heavy rainfall, the cloudbursts are happening. When they occur, so you have a reasonable different disasters which are happening downstream. Is could be a flash flood, a lot of sediment or erosion happening, and eventually that causes the landscape changes, which eventually has a lot of implication in the sediment transport, and specifically more onto the bed load, which is the material which is lying down in a river system which moves along the river. That is important, and that really makes a very huge changes in the stream morphology. So I'm going to talk majorly on two aspects today: on the sediment transport, which is mainly the bed load transport in the high gradient rivers like in mountains, and also what exactly changes and why and how it is changing in a river system in terms of the morphology. So there are very few pictures quickly. So why we are talking about? So these are the events which are very frequently occurring. That was 2013 Kedarnath flood. We all know, and people might have studied also that this happens in the Kedarnath area, and which causes a lot of flood, and then there is a lot of damage downstream happening to hydropower as well as to the human lives also. That was 2013. 2021 is Chamoli event. Again, people have studied about it, and again we have a lot of changes to the morphology happening. And this is what makes it very, very interesting as well as very disastrous is like, how do you really measure this type of sediment which is moving down into system, and how can you really estimate those numbers which is basically sitting there? That was 2021. A very recent one which has happened in the Sikkim region. Again, a huge implication on the hydropower and and also the downstream people. So all stating that, and this is only from Indian side, but there are other events which are occurring all world around. So when we talk about this set type of sediment movement, it is not only coming as a just a sediment movement. It is the governing force will be basically the water which is carrying out this system, and it is basically the river discharge. When we talk about river discharge is important because we need to know how much water is coming into a river system so that we have hydropower or the water reservoirs to supply water downstream. Also for the hydropower generation and also about the sediment transport. But so this discharge estimation is important. But these are high gradient rivers. How do we measure it? Traditional methods to measure the discharge in this type of high gradient rivers are very, very hard. It can bring a lot of errors also, but very, very time consuming. So there are methodologies which are basically coming up, and it has been in the hydrology history also that there are methods which can be utilized towards discharge estimation using the entropy theory. And that is what I'm going to talk about, and how we have used that entropy theory towards the sediment transport, especially focusing on the bed load movement. What we do it is like, so there is a methodology again from the Department of Hydrology, one of our PhD student, who were basically developed a methodology using a single point velocity measurement using the entropy theory to get the velocity distribution in a river system. So we built on that. So we used that one point velocity measurement, calculated the discharge velocity distribution over a cross section in a river, and using the entropy theory, we moved into the sediment transport, especially in the bed load transport method. So I'm going to talk about this case study very briefly. That so we did this study in the Alaknanda Basin, which is again a very Professor Bonster talked about the Alps and the region where we have talked about 300 or 400 square kilometer. This system is a huge system. It is of the order of 10,000 square kilometer. And we use the discharge measurement done by the Central Water Commission (CWC). Using they used the current meter, the traditional method, to get the discharge. But there are methods which can be also non-contact, where we you can just use the from the without touching the water, you can take the velocity measurement and the depth measurement. Using that stream flow measurement information, we developed the entropy concept towards the sediment bed load transport model, and then eventually we extrapolated and we saw, okay, how much bed load is moving in this system. So the system is around 10,000 square kilometers, sits in the around the upper Ganges river system. And so we basically did the measurements, and the CWC data set we used is at the Srinagar station to start to apply the entropy method. Very recent, last year, or maybe early this year, April or June, this is a type of material which is lying down after the event. So this is of the order of April 2024 event. Just a normal low flow condition, still a pretty good high flow, 350 meter cube per second discharge, but a lot of material which is lying down here. And this is when it starts moving into this river system, it's moving as a sediment transport. So what we do is basically you can do the discharge measurement. That's the starting point. So you get the flow velocity, what is happening in a river system. You can do it with the current meter, which the Central Water Commission uses. You can also use a ultrasonic method to or the sensors to get the flow velocity, or you can also use the ADCP, which is a nowadays a cutting edge instrumentation where we use the boats to get the the velocity profiles in a river system or a cross section. So you use that and you get the velocity. So that velocity, we basically used a single point velocity measurement to convert that into a 2D, two-dimensional velocity distribution. So the 2D velocity distribution is simulated by maximization of the entropy, which is basically knowing the maximum flow velocity and the geometry of a cross section. So what you're seeing here is the Chu 1988, which gave us entropy theory concept. Here, what we need to really focus on this is these are the equal velocity profile. It's longitude the cross section across the cross section. And what you see here is in the longitudinal side, so basically you have some high velocity coming up in this region. So he used that maximum velocity and the entropy concept to link it up to get the uh, ratio of the mean velocity and the maximum velocity and express it into the entropy coefficient. We use that. So what you do is basically you have a velocity profile which is only at the one single point, and you distribute that vertically as well as horizontally. So you are basically distributing the velocity profile in vertical, which is a function of the surface velocity and the dip, because in vertical profile, the velocities are maximum at the certain depth below the surface. So you get that vertical profile, but also you use the one velocity measurement to also do it at the longitudinal one, the cross section. So you convert that. So the Tommaso Marco from IRPI CNR, Perugia, he developed another concept of velocity distribution longitudinally. So we use that and basically utilizing the parameters of the water depth, the dip parameter. So you calculate that overall, the whole longitudinal profile. Using that, so you get the U max and the ratio of the U minimum and U maximum. When you use that concept, so you move that. The focus is that you are able to calculate this the entropy based U the velocity profile. Using the U entropy based velocity profile, you're able eventually needs to calculate the shield parameter, which is going to be used for the sediment transport. So, and any sediment which is lying down in a river system, it has it has to overcome a particular critical friction or the critical shield parameter start moving into river system. So it has it's a drag friction force and the gravity force, which is basically lying down on a particular sediment which is lying and sitting on a riverbed. It has to overcome that to start moving up. So it has to overcome the shield parameter, which is critical. It has to be more higher than that. Using that, so basically we calculate the dimensionless Einstein bed load parameter or a number. which is again a function of your critical shield parameter and the shield parameter which is acting at that particular sediment. So we use that, and then we calculate the dimensionless steel bed load transport, and then eventually you can apply that onto different methods to get the sediment bed load transport which is happening in that particular river section. So starting from the Umax or the velocity profile computation towards the entropy based velocity profile, and then the shield parameter, and then you calculate the bed load transport in that particular section. When you do that, so basically what you are getting is this is a type of a cross section of the velocity profile in terms of high flows in that system. So the in general, when we talk about the vertical profile of a velocity in a river system, in vertically we normally follow the logarithmic profile, but in the longitudinal there are two methods, or the distributions are normally being accepted, is the parabolic or the elliptical. So we tried that to just see what are the different errors in elliptical, the velocity profile, and the parabolic velocity profile. So there are some errors coming up, but in general, the elliptical is giving better results in 2D velocity profiling. Using those velocity, we put it up in a simple distribution for discharge estimation using the entropy. So what you're getting here is basically using both the distribution, 2D parabolic and elliptical, low flow condition, medium flow, and high flow condition. What you see here is at a low flow, the numbers are little off, the errors are little higher as compared to the medium and high flow. And why it is so? Because at a low flow conditions, there are more losses which these entropy based models are not able to capture. But in the high flow and the medium flow, it is able to capture those losses. So that is the reason. So the errors are less. Using those minimum velocity, we calculated the discharge, which has been compared with the CWC measurements, whatever discrete data we have from the CWC, to get how good they are, and they were pretty reasonably fine at a medium and high flow conditions. Using that, then we started plotting the shield parameter, the shield parameter and the shear velocity, which we calculated using the entropy, and eventually the dimensionless bed load Q star, small q star. And what you see here is basically this. We also use a Miller methodology in 1977, which is very well accepted for the shear velocity, which is very well coming up onto the low flow conditions. Then eventually what you're seeing here is the bed load transport, which is reasonably fine as compared to the other parameters. So the overall bed load transport, what we calculated, so what you see here is the parabolic based bed load transport, elliptical with the squares. So they are very much matching up with the other methodologies, but still better than, because other methods which are Mayer, Peter and Mueller, Parker and other methodologies, they are basically underestimating, or sometimes, yeah, eventually more of the underestimating system. So bottom line, what we want to show here is that the sediments which are lying down in the river systems, which have come from various different type of hazards which are happened or disaster which has happened, they are still play a very significant role in moving and changing the sediment transport in a river system. Quick example, it's a longitudinal transfer distance across a cross section, and the u velocity, the shear velocity. When you see here, the maximum is somewhere in between the 10 meter to 125 meter. So it's the section in between the river cross section where you have maximum the shear velocity is happening. Based on that, your velocity, the shear velocity, and then eventually the bed load. The bed load is happening somewhere around where you have the maximum velocity happening in that particular cross section. So major goal is, okay, there are high flows which will carry a lot of sediment, which a bed load, which is known. But what also it's interesting to see, this small hump in a small, very low flow condition, there is still a lot of movement of sediments which are happening, and which is also a very significant system which is moving in this high gradient rivers. Just to quickly summarize this part of it, is like the single point measurement of velocity can be utilized towards the 2D velocity distribution that eventually can be utilized using the entropy method to get the sediment, and were pretty consistent with the other methods and the models which are available. But as Professor Bonston also mentioned, that there is a huge scarcity of observation which still needs to be understood to understand fully the overall sediment transport. Last 2-3 slides, we also have recently seen that there is a Sikkim glacial lake outburst happened, which happened in Sikkim, northeast state of India. And this is the lake, and this is the notch where the lake outburst happened because of the material moving down. We just did a very small preliminary study on that, how the sediment has moved downstream. So we did not talk about what happened actually in this part of the lake. We did some basic analysis of remote sensing. What happened when the sediment has to the morphology of a river system? Lake outburst happened here. We are talking about this part. This is almost the boundary of Sikkim and West Bengal. So we focused on, yeah. So we focused on this component of like this boundary of yellow line in the river section. We use simple remote sensing methodology. Use couple of satellite imagery, multi-temporal, multi-spectral satellite imageries using the GE methodology, and did some of the basic remote sensing calculations to get the MNDWI as well as NWVI to get majorly the active river channel, which is nothing but the sum of wetted channel water pixels and the non-vegetated pixel, which are exposed sediment. And using those some of the thresholds developed by Boothroyd, basically to get the how the river channel has moved. So this is a picture before the event has occurred, and this is the part only which I'm talking about, the West Bengal boundary of Sikkim, Loud Stream. So basically this is, if people know about it, so it is the Sivok area, and this is the part in Jalpaiguri region. So this is around 50 kilometer stretch of that river. After the event has occurred, the accretion of the sediment has basically huge in number in both the bank side. And this is a pictorial from the field. A huge amount of material has basically deposited on both sides of the river's cross section, and you can see a picture where almost the bus is subsided by the sediments. It's not that. So when the system occurred like that, when the sediments are there, there is huge recent happened. It is almost a effect of the event which has occurred in 2023 in the Tista region, right, or in 2024. The material. So this is a landslide happened in August 2024, just a couple of months back, and it is mainly what we are hypothesizing is because a lot of sediment which has been there in the river, the morphology has changed. When the monsoon came, July, August, the monsoon came in that region, the water does not have space to really move. So it starts undercutting the sides, the banks. And that is basically a lot of huge sediment, the landslides happened. So the bottom line is, yes, there is a lot of sediment lying down, but it also has a lot of compounding effect in a long term. So with that, a small liner from my side is the disaster not only have instantaneous consequence, yes, we can see it, but have long-term implication and may compound the effect of the upcoming disasters if we do not really manage them prepared, or we are prepared for that. Thank you very much.